Great. Okay, so here we go. I'll start off. So, welcome to more of the Wolfram Technology Conference. I started yesterday giving a talk on the Wolfram Compiler and progress and some of the things that we can do. Mark Safroniou gave a very nice talk on some of the arithmetic systems and sort of optimization features and things that we had. And today I was going to give another talk looking at some ideas of high performance computing with the Wolfram compiler. So I'm just going to run through some, just in case there are a few people that weren't at the talk yesterday who are here today. Just a quick refresh, the compiler. It's a compiler for the Wolfram language. It's a long-term project that's been going for some time, and it's entirely built in the Wolfram language. And some of the things that it can do, the fundamental thing is it converts Wolfram language code into native machine code that's very close to the hardware, the metal, the CPU instructions. It uses LLVM as a backend. It has an in-memory JIT compilation mechanism, but it can also generate dynamic libraries. It uses static type annotations with type inferencing, and it's an alternative execution model for Wolfram language code. So let's just talk about performance computing. There are, the fundamental thing we need to do is to make sure that the code we're generating is fast, that it's comparing well with handwritten C or C++ that's compiled with other compiler systems like GCC or Clang. There are some special program transformations that can assist performance computing. Automatic differentiation is an example. And then there's various technologies that we can take advantage of. Multi-core, CPUs, grid computing, and GPU computing. And I'm going to try and talk a little bit about all of these in the time that I have available. So first, I just want to talk about code optimization. So this is automatically rewriting code so that it's faster. It might mean that users take some decisions to relax the requirements, sort of turning off safety measures that sometimes can be beneficial. And it might also mean targeting special tools, libraries, and hardware. And just to reiterate, the basic pipeline of the compiler is that we have a Wolfram language phase of it, where we start with Wolfram language code and we generate an intermediate representation, and then we process the intermediate representation with various transformations. Then we hand it over, we generate an LLVM intermediate representation that does more work and generates machine code. So the Wolfram intermediate representation is pretty close to the native machine code of the platform, but it has some differences. So one difference, it has type markup in it. That's quite useful for figuring out intent and verifying the code. And again, and then there's another detail, and this is probably too technical to go to in the moment, but it's written in a certain way that has some important mathematical properties that make it very suitable for transformations and such like. And so in the sort of optimization, some of the standard techniques that are done are things like constant propagation, constant evaluation, eliminating copies, eliminating code and branches, and inlining code. And a lot of the optimizations that we do, these get run over and over again, trying to reach sort of optimal code. Now, we have a few transformations. There's potential for optimizations and work that's special to the Wolfram language, that's based on knowledge of the Wolfram language, like fusing operations or avoiding data copying based upon Wolfram language semantics. And then there are other things that are more general, lower level transformations that LLVM is very good at. And there's a lot of functionality in LLVM for doing things like that. There's a lot of loop work, so lifting things out of loops, eliminating loops. And this is super important because even though actually the loops run quite fast, they interfere with an even lower level of the CPU because they interfere with pipelining of instructions. So when you hit loops and branches, that can cause problems with optimal code. So if they can be eliminated by analysis of code, that's going to be quite useful. Right. Oh, there's just a quick question about the new Intel Mac. It's already working. So we have the compiler already working on the new ARM Macs. That's a benefit of working with LLVM. So we're up on the game for that. But let me just give an example of a transformation that's special to Wolfram language. So I've defined a function, and then, so in this function, what's been written is I've got, you know, one list, and I'm adding it to another list. So in the, and this is done actually at the AST, the syntax tree level, is it's actually done it's realized that I'm adding two lists that have the same dimensions. And so it's eliminated them and it's turned them into one list. And actually this makes a huge improvement in timing. We don't have to bother making a list is kind of expensive or something. So that's type of a performant transformation. There's another type of transformations that involve relaxing requirements of the system. So you can avoid validated. We both Mark and I showed some examples of this, avoiding validated arithmetic or abort handling, things like that. And just remember that a lot of special hardware like GPUs, they already are relaxing your requirements. They're running in a different arithmetic model than you would get from just the sort of, you know, precise CPU operation. So now I'm going to look a little bit at using some multi-core HPU. So what this is doing is this is still an experimental thing, but this is using concurrent code running in multiple threads. And these are some tools that we've been developing to make use of a technology that's commonly supported, that's called OMP. And one of the key things, a couple of key things to mention is that running code in concurrent code in multiple threads with uncompiled interpreted code is simply not possible. This is code, not like individual functions, but writing Wolfram language code that runs concurrently is not possible with the interpreted code. And these new tools, people ask about this, they have a lot more flexibility than the old parallelization option. And I'll try to show you some of this. So here are some of the things that we have. So we have, for example, a parallel map, and we start out with a list and we partition it and work on individual parts of it in threads, and then populate the result. We wait for everything to complete, and then we can finish. And this is all on one machine. And so we have like this parallel compiled map, and we can launch this. So some of the compilations are a little bit slow, but they get faster as the time goes on. And then, right, so there we go. And so this, I'm giving this is like 100 million data elements, and we can process this in a well, you can see how, the speed that this is running at. So now I'm generating a sequential version, and on the same data set, it's running, quite significantly slower. I've got 8 cores on my machine, so this is getting up to the sort of optimal speed that we might have from this. And just to give another, if I come and run, I need to take a function here, and I run this, and actually I'm running this on, I'm taking only 100th of the, so really you should multiply this number by 100. So this is actually running in the old compiler. It's going to be, so this has gone, very significantly faster. Right, let's have a look. Right, parallel fold. Again, some slightly more technical questions. Adding an inquiry. Right, there's a question. I'm just answering some questions as we go along. There's a question about a CUDA replacement for macOS use with the machine learning modeling. That's a question. I mean, there are alternatives to CUDA on Macs. So the basic problem there is that Apple and Nvidia have no working relationship, and so there's no utility of any Nvidia hardware or CUDA programming on Macs. You need Linux or Windows for that. I believe that the underlying MXNet, the machine learning framework, is pretty also tied into CUDA. So at the moment, there's not a good solution to that. Are there good tutorials for writing parallel compiled code? Some books have guides, but not nearly into this depth. Yes, I think the answer there is that we should be. These tools are still not quite the prime time, but I'm a big believer in writing tutorials, and if people are happy to contribute to the effort, that's fantastic. So there's all sorts of ways of contributing with this, and that's really useful. Right, let's talk about a parallel fold. So this is basically you have a list, and then you partition it, and you do work on the individual parts, and then you do reductions. You might do several stages of reductions till you get a result. So this is we can sort of set this up running. So this is a bit like fold over a data set, and then we run this, and again we get a nice accelerations for this. Again, the sequential version is running quite a bit slower. So we're also getting the same answer, which obviously is attractive. Here's another construct. This is a parallel table, and this is runs. So you give it a small input, but what's quite useful is to give a large input. And again, this table instruction, we're getting, some quite nice accelerations in this. So one of the things that works quite well with these parallel constructs is we're making a big suite of different styles of parallel constructs where you don't have to worry about the actual details. And I thought this might be an interesting just to work through an actual example of, and this came from some user code that somebody sent in, and they were trying to do a Mandelbrot computation. And this was their code. So they made a compiled function and they ran it. Very little. There's a question here about how much mathematical system is dependent on Java. Not very little of the now some of the connectivity code. So there's like a toolkit for working with SQL databases that can use Java. But we've been steadily working to avoid that. Right, sorry, I'm jumping back and forth. So here's the computation, and it ran in such like. So, and this actually is running faster than in 12.1. Now, here I'm taking the same code that I had there, but see, this has an inefficiency because I'm generating a table and then I'm mapping over the table. But really, it's much better just to put the table inside the compiled function, and then I only have to make the data once, and so I get some. You know, this has got a little bit faster. Again, sometimes it's better to run these. You can run these things. Sometimes they need to sort of warm up the underlying LLVM JIT system. Now I'm going to take the same example, and I've replaced the table with a parallel table, and this compiles, and this runs, and so now we're getting like a serious parallel acceleration. We've gone from 1.2 seconds down to 0.2 seconds that we've generated. Yes. So one of the things that this does actually is this is fusing. There are two iterators here. It actually fuses both of them into one iterator and does all of that in parallel. So just a little description on the benefits of this multi-core. It's very easy to set this up because your platform, your computer already has multiple CPUs, and communication between them is pretty fast. It's the speed of basically memory accesses, which is in some ways it's slower than retrieving from CPU crashes. There's no grid no grid launching. There are still some issues that we have to work through of how to propagate errors with exceptions and memory management that we're still resolving. And this is why this is still an experimental thing. Right. Now, so someone Nick White gave a thumbs up for grid launching. Of course, that's what I'm going to talk about now. The grid launching has its use as well. So I actually have in my, I keep a few, actually I have lots of computers, but I keep particularly Linux and Mac and Windows because I need to check that things work on that. And I have a little network, need to keep an eye on the time. So this is the grid. So I've got my main machine and I've got a couple of workers. And the idea is the main machine sends out commands to the workers, and then the workers send a response. And Mathematica actually comes with a system where I've got, where you can set things up. I set things up to launch the kernels with SSH, and actually, once I got the SSH connection working, sometimes in live, there we go, that's all working. It's actually quite robust and such like. So I have 4 kernels on a Windows machine and 4 kernels on a Linux machine. And I do parallel evaluate, it sends the same command to everything and reaps the result. So I thought about a way to integrate this with the compiler. So the compiler has a mechanism for making dynamic libraries. So what you do is once per machine, you send a command to one CPU on that machine, each machine, to compile some code and make a library for that code. And then on the machine, each kernel then loads, each CPU loads that library. And so I thought that was an interesting workflow. And I wrote some code so we can set that up. And so we initialize the system. And so the main kernels, these are the kernels that are going to do the compilations. And so now what I'm going to do is I do this. So this is contacting one kernel on each machine to create a library. And so it has to initialize, and then it loads that library into each of the kernels. And I can, this is just like x+1. One of the things I set up, which now, hang on. Sometimes I hit the wrong key. Right, was I set this up. So this, the name of the function is defined on each worker, but it's not defined in the main system. And that's quite useful. And there's a common snap, you know, it can be a snafu in the parallel toolkit in that you send a command, it doesn't actually execute remotely, it comes back and then executes locally. So it looks like you've got the right answer, but it didn't do what you intended. Now I'm going to show, this isn't a totally exciting example, but this is some sort of Monte Carlo computation. So I'm generating, you know, a random number, and I'm going to then iterate, do a number of iterations to, you know, see if it's, you know, I'm basically computing pi. So if the result is less than 1, this is based upon, you know, the area of a circle, then I increment the counter, otherwise I don't. And I'm using the nest operation. So I've done the computation there, and then I've sent to the workers, I've sent the result coming back there. So this is, okay, right. So I'm getting a question here. Maybe I might answer that. Well, basically the plus, the reduction function, you do the parallel. Okay, I'll have to go. So maybe I'll answer that question at the end. I don't want to run out of time. So doing this computation, it's slightly better to do it with the parallel submit functionality. So what this does is this is a little bit more asynchronous. And so here I've submitted a number of jobs, and then it's waiting for everything to come back. So this is another quite nice way of using the compiler with the grid technology. And just going into the grid technology, it's good for scaling to very large systems. It's good where the jobs run very independently. So if there's a problem with one of them, it doesn't bring everything down. And Mathematica has quite a lot of built-in functionality for working with these ad hoc grids. So that's kind of an interesting functionality. Right. So let's come and look at another HPC functionality. And this is transforming programs. This is automatic differentiation. And it's a bit like symbolic computation, but because of various technical details, it's very suitable for HPC. And also for technical reasons, it fits very well with this intermediate form of the compiler. And so here, what we do is we take a function, and what we're doing is it compiles it into this sort of intermediate form, and then it does transformations on it, and it generates a new function that will return the value of the function and the derivative. And it's a projection of the Jacobian. It's really more suited to sort of very large multivariate systems where you've got thousands of input variables rather than just one. But I did this just with one, just because it's slightly easier to sort of see what's happening. And so now I'm going to compute the derivative for a range of inputs, and we can see that actually we've got quite a good rendition of the result. Now this was slightly cheating because the function I had here was just an elementary function, and so it knows how to differentiate that. But here's an example that's slightly more unusual. I'm going to take a series expansion and generate a function and compile that. And so this shows me, so it's not a bad, I've got 9 terms in the series. Of course, if we go a little bit further on, then let's talk to the analysts, and they'll tell us, what the range of convergence of this series is. And just out of FYI, this is the, again, this could probably be written in some more efficient form, but this is showing what the function actually is. So now what I'm going to do is I'm going to take that function, which is just written as a sequence of elementary functions, and I'm going to I've differentiated it, and now I'm going to do the look at the output. So again, just FYI, the output is going to be right. So it says, if the input is 0, then the output is 1 and the derivative is 1. And so here's the differentiated result. So this is actually from a purely elementary thing. It's able to generate the differential quite effectively. And there's other technical benefits. It's actually computing the value and the derivatives all in one computation, so it can share various, optimizations and things in the middle. So this is, very relevant for HPC. Many computational problems need accurate, if they've got more accurate derivatives, they'll be able to generate a result. It's a bit dumb in the univariate case. It's good to see it, but it gets particularly beneficial with multivariate functions. Right, now I'm going to talk a little bit about GPU programming. So, just a quick rundown. GPU programming is using graphical programming units for general programming. And typically, GPUs they have huge numbers of CPUs, but the CPUs are not quite as flexible. I mean, they're Turing complete and everything, but they're not quite as flexible as the CPU on your machine. Nonetheless, they can be used for certain types of computations, and they can give massive accelerations. They're non-trivial to set up, and the code that runs on them is subject to incredible constraints, which also makes them non-trivial. A particularly popular GPU system is known as CUDA, which is the programming language, the system that runs on Nvidia hardware. I'm going to have to keep going fast and run out of time. And it has this little model. You have your CPU, and you offload the data, and it goes through this sort of complicated, you copy data, you run the kernel on the GPU, and then you copy the data back. So we have a thing called CUDA Link that's bundled with the Wolfram language for a long time, but now we're starting, I'm not going to evaluate these, to build a link based on the compiler to Nvidia tools. So we can just, since the programming language for, Nvidia provide a C interface, it's very easy to set up compiler bindings, and it's the same game plan as, what we did with OMP and things like that. And so we just make bindings to these, and then we could write functions and compile them. And they run in the same way as if they were being called from C++, but since they're integrated with the REPL system of Wolfram language, they're very convenient. So then we need to generate a CUDA kernel. This is the thing that executes, and so you typically write something that looks like this. But what's new now is that we can convert this, do code generation on this, but we can generate the PTX, the language that actually runs on the GPU. So with this, we've gone from Wolfram language, a Wolfram language specification, to something that executes on the GPU. Then we need to use this, we need a driver program, and don't need to look at all this, but this is doing the copying. We can compile that, and then we can execute it. So I've used here a numeric array input. I pass this driver, the program and the input, and we get back the result. So that's the idea, is that we're looking to integrate the CUDA link with the compiler. And this should significantly lower the barrier for working with GPUs. And it'd be feasible to do this with other systems. And this is kind of a nice interactive new workflow, is that you can prototype GPU work interactively and then compile it all to combine it all into one function and compile it. And I think I'm just about out of time, so I'm going to give a summary. So I looked at some issues of performance computing, possibilities from the Wolfram Compiler. I looked at code optimization issues, some multi-core computation, grid computing, automatic differentiation, and GPU programming. And again, I'll just reiterate that we have a lot of opportunities for developers, interns, in various flexible ways. So get in touch with us if you're interested in coming to work on this. So I'll just answer a couple of questions that came in. I will share the notebook out at the end. Yes, it's possible to generate standalone executables. And if you have them, you might or might not need the Wolfram engine, depending what your code does, but it's entirely possible to make things that run entirely independently of the Wolfram engine. The GPU compilation does not require NVCC. It requires the CUDA toolkit because that has some bindings, LLVM bindings, but it's purely based upon LLVM. So it's not running the Nvidia compiler. And then there was a question about if fold is associative. Right, so what you're parallelizing is, I'll just go back and try and show you how this is working. There's a fold, actually, you can think of fold as, here's the fold. There's actually, or maybe I'll just show this. So in fold, you do something like, you have a function that takes one argument. That's so in fact, what you're doing is you have like a reduce function and a map function. This is kind of another way of thinking about fold, you see. So this is plus in here. So what you're doing is you're assuming that the reduce function can be run multiple times. So you have some constraints upon the type of the reduce function. But again, this is a compiler, so we know the answer to that. So you have knowledge from the compiler about the details of your functions. So since you allow tying in CUDA, yes, I think there'd be a lot of possibilities for tying in some other toolkits and things like that. The compiler is incredibly useful for making very performant interactions with other technologies. You compile Neuro with the compiler. Right, so there's a question about MXNet and compiling so it can run train without MXNet. That's a slightly technical question. I'm not an expert in this. MXNet has an awful lot of machinery and types and things that are quite convenient. The automatic differentiation is itself useful for MXNet. So that's all. Especially if you want to write your own layers or your own additions to things, and that's quite useful. I tried generating a shared object, was not running by calling the library directly. I'm not quite sure what that question means. So, but I think I should probably wrap up because people need to get onto other talks. Keep sending questions, and we can answer this. But thank you very much. Thank you.